Today we will have the last real lecture with new content, and last but not least we address the idea of validation of our network model. That's often a question that is asked: how do you know that the network model is valid? Or for any model, that's often asked, that question. And in this case we get some answers for that. And also in the assignment of today you will learn to use some methods for that. So today, probably it is about 20 minutes, 30 minutes, or maybe a bit more. I will first discuss why can you tell that a network model is valid. And then I will continue with a number of techniques that can support you to get answers on that type of question. And the first question is, how can you justify in general that the network model is valid? And it has a number of different elements. The first thing is always that you have to make the model, to design it according to some type of knowledge that has some empirical justification. So you study some phenomenon and you find out what the underlying mechanisms are for that phenomenon. And then you look in all kinds of scientific disciplines that are relevant for it, so like neuroscience or social science, health sciences, whether you find such knowledge or theories about such mechanisms, and then by including them in your model, you have at least some scientific justification that the structure of your model relates to those empirically founded elements. So that's one thing. You should never forget this part, because often the emphasis is more on the second part that I will discuss next. But this is always important, that you can refer to literature why you have a connection here or a connection there, or why did you use a high threshold value for a logistic function if you want to model a high pain threshold, for example. So references are always very important, that you can justify a model by that. But then, of course, also the outcome of the model can have some justification. So you study some phenomenon, and then you would like to show with the simulation that indeed that phenomenon occurs. So that's an important thing. If you make a model for emotion regulation and the emotion is not regulated at all, yeah, then you fail with that. So you should show that the emotion indeed is regulated after some time. So for that, you already know that you need some settings of the models in the characteristics in the role matrices that fit well to the context that you're modeling, for example, some type of person. And that can be not so easy, so that can be a difficult puzzle. So finding adequate values for that is part of the experience you build up, and to develop some intuition for that. So I think many of you already have improved that intuition in the meantime. But there is also a technical way to support that. And of course, we could have addressed that the first day, and that you never had to choose values yourself, but that's not good. Then you would never have learned to do that. But there is a notion that's called parameter tuning. That's further the main subject of today. That can be helpful just to find the right types of values, or at least adequate values. So the idea is that you have some actual system in the real world, and some observed behavior. Then you make some dynamic model of it, and then you have behavior of that model, and then you compare it. You compare the graph of your predicted behavior as the model simulates it, and what you observe in reality. And then if you see some differences, you want to give feedback to your model, that you improve your model, that these differences become less. That's the main issue, what we do today. So you run your model, you see whether or not it's a bit okay, and where it's not so okay, you try to really set your model a little bit so that it becomes better. And for that, you can get now some support. So that's also important, that you are able to formulate what your model should do. So this graph, you never get it, almost never, from your domain. So you have some idea about the graph, but so you still have to explicitly formulate that to be able to see when the model is a bit okay. Because if you even don't know where you aim at, yeah, then it's difficult to say whether or not the model is okay. So therefore, it's always important to formulate some form of requirement or required pattern what the model should fulfill. And therefore, in many of the assignments, we have a separate part of it to ask for that. But that's also here important. So that's the general idea. And these requirements, they are the most important norm that you use to aim for. Because the direct measuring of the characteristics for a model is not possible in general. You cannot measure how strong the connections between two neurons are or two areas in the brains are. So all those things usually cannot be measured directly. You only have indirect data, like to what behavior does that lead. So, but that's also part of the model. So that part of the model, you can compare it. So there is a large scope of a network model. So you should be aware of that because of all these different characteristics that can all have their own values. You can have many cases that you can address by your model. So for example, you can address people with a high pain threshold or with a low pain threshold. You can address people that are good in emotion regulation, people that are bad in emotion regulation. So there are all kinds of variations of persons that can fit in the model. So that's not a bad thing by itself. That makes that the model is really useful for many cases. But on the other hand, if you want to model one specific context, one specific person, you should know how these values should be set. So that makes the search space, the big search space, and that you have to find some specific place in that search space in general if you model one specific situation. So suppose you have 10 things, 10 parameters in the matrices, in the role matrices, or you have more of them even usually. And you want to have, you consider only one digit, like 0.1 to 0.9, 10, and 1.0. Then the number of combinations is already this one, like 25 billion. So that is, gives you an idea of the search space where you search for your values. So maybe this gives also some understanding why it's not always so easy to find values directly, but often it's after a while you can still find good values. Still also because you have types of heuristics in your mind after some experience. But now we will do that by support of technical means. So you have many situations, persons can be modeled, but how can you model one specific situation that you want to address? Which values are there? There are multiple solutions also possible, because one behavior, there can be different brains that can lead to the same behavior. So there is not a law that says one behavior that can only be done by one brain. That's not true. The brain can have different variations that can still lead to the same behavior. So therefore, you have to keep in mind there are usually multiple solutions, and that's not bad, that's just acceptable. And then you can find one or more of these solutions if you want. So choosing the appropriate values of the characteristics. So now we call them parameters, because in the area of parameter tuning, they are called parameters. Don't confuse them with the parameters of the combination functions, because they are just a subset of this. So connection weights, you can have 0 or 1 for lower or higher effect, or for negative effect, -1. You can have speed factors that have different values. For example, for bodily changes, you can have a lower speed factor, and for internal mental processes, a higher speed factor. So all these things have their own variations and can have their own effect because of these variations. Now we have to find out how much a model differs from some reality, some real situation, and therefore we need measurements of errors. How far is the deviation different? And how far does the model deviate from what you expect it to do? So therefore we have some norm, there's the root mean square error. I will explain it in a moment. So you have required or expected values, for example, based on empirical data, but maybe it's just that you only have qualitative information, empirical information, and you express that by higher and lower numbers in values, like it should be a high activation, then you say, okay, that's 0.8 or 0.9, and if there is almost no activation, it's 0.1. So you can express that in values, that's the idea, because it's a numerical method, you need values for it. And then you have, so on one hand, the empirical data, and on the other hand, there's a simulation outcome. And then you compare them. So the deviation is with the model, the simulation data, minus the data from the empirical side that you have put yourself as the expected pattern. So this is even a bit similar as we did in the previous assignment, the deviation between different things by which you compare. That's not really different. But now we do it still in another way. We compare these things, so you have to make them as small as possible, but there are multiple of them. You have different states for which you have data, probably, and you have different time points for each stage for which you have data. So there are a number of them, and if you make one as small as possible, maybe the other one is not as small as possible anymore. So therefore there is a kind of averaging and aggregation form. So these are the simulation data, these are the empirical data. I put them in this formula here as model data and data. And this is, for example, one state in the model for which you have data, and this is another state. I consider now two states. And there are also two time points. One time point T1 and the other time point T2. So you have actually four different data. So for the time axis, you have in that dimension you have two, but also in the dimension of the states you have also two. So 2 times 2 is 4, and therefore you make you divide this expression by 4, and this expression is also called the sum of squared residuals. You can forget it because we always use this now. But some people in the literature use that one. Then you just take the square of the difference of the deviation, and then you add them to each other. You make just the sum of all 4 of them. So these two, but also these two, you sum all of them. And because they are 4, if you want the average square, then you have to divide by 4, and then you take the root. That's the meaning of root, mean square error. Mean means average, and you take the squares. And these are the squared residuals. These are the residual differences. So these are then that sum. So this is built in our approach to parameter tuning. And then finally, you want to change your model in different iteration steps so that this error starts to become lower. If the error, for example, is 0.5 in a 0-1 interval, that's almost that's half of the interval. That's too big. But if it's like 0.2 or 0.15 or 0.1, it's already a bit okay, because this is kind of averaging of the deviation. So this deviation is averaged here in this type of aggregation formula, which is actually the Euclidean function if you look well, and then or the true Euclidean function, but that's a separate thing. So if you get this low, then you are a bit happy. Lower than 0.1 or 0.15 is always difficult because your data themselves, they have their own variation. They are never very clean. They often have the fluctuations, and your model will not follow the fluctuations because you don't even want that, because then the model would not be so convincing. So therefore there is always an inherent deviation because of the empirical data have their own deviation already from kind of what would be perfect for them. So therefore, if you have a value here like 0.15 is very good already, a 0.1, and maybe in many cases 0.2 is what you can maximally attain or optimally. So that's what we want to do, and I will show now some techniques to do that. So you have a large number of iterations, you have two parts of the process. You have some part that generates parameter values, and they are denoted here by P1, P2, P3, so values for a number of parameters of your model. And you do it, every iteration you do that again. So it goes like this. They are fed to some model environment. So we have a separate template for that. It's called the tuning template. And that's running, and then it gives feedback to this, and then it goes on and on and on like that. So then you can do 5,000, 10,000 iterations easily, because it's very efficient in general. Especially now we have computers that are also very high performing processing. So that's the idea. You have two things that are interacting with each other, and this is the boss. You start this one, not that one. This one, the template for tuning that we use, it cannot even be separately activated. It's only if it's used by this one, because it needs these parameter values as input. So if you try to directly run it, then it misses this input. So that's the main picture. You should always keep in mind this type of picture. So one example is brute force by exhaustive search. That's a very simple method. You enumerate all possible values with a certain grain size, and then you look at all of them what the error is. And then you find the optimal, the global optimal form. So that's always a good solution. The only thing, it's a lot of work. That's a bit pity, but at least if your number of parameters is not too high, then you can do that. So it fulfills, whether it fulfills. If it does not fulfill, then you just check the error function. If it fulfills, it's okay. Then you find the options for the values. I have an example here. Suppose you have two parameters, and you have a grain size of 0.1, so you only distinguish at that level. And then for all 100 cases, you do the simulation. And this is actually not the root mean square error, this is the SSR, so because the numbers are not between 0 and 1. So then in all these 100 numbers, you see one that is the lowest. Well, that's the global optimum, that's the best match. So therefore you have a very good solution. But now you can say, yeah, but now I want to say, I only see that one should be 0.1, the one parameter, and the other one 0.3. But I want to know more. Maybe it should be 0.35 and 0.05 or something like that. So then you could refine it, but then for a smaller interval probably. But then you still have to do more work. So this is a good method. But for more, this is even only 2 parameters. If you want to use for more parameters, it's not so good. So these are the advantages. Easy to do it, implement it also. You have all combinations are explored, and always find the best set globally, best set of values. And it can be a kind of baseline method to compare other methods to it. But there are, of course, there are also disadvantages. So if you have only 2 parameters, then you have already hundreds of things, 100 at least. And if you want to do it an accuracy of 0.01, then of course the number becomes much bigger, many more zeros behind it. So the computational cost is proportional for this number of assignments. So for practical problems, it's a bit quickly, it's a bit impractical, I should say. But for small numbers, you can always use it. So another one is gradient descent. Actually, this is a principle also behind some deep learning, some popular deep learning methods like backpropagation in neural networks. So the principle is a bit simple. You look at how sensitive the error is if you change some parameter value. So if you have a parameter value and you check what happens when you change it a little bit, like 0.05, for example, you add to it, or minus 0.05. And then you look, what does that to the error? So so if the error has a big change, that means that the error is very sensitive for that parameter. So that's a good information, and that's what is used in this gradient descent method as well. And if you have parameters that do not change the error, if for example, if the error is only changing like this, very small part, then that parameter doesn't matter so much. So you better can focus on the other parameters. So that's the idea of this method. So then the sensitivity, that's just the difference in errors when you change the parameter a little bit. Be aware that sensitivity is very context specific. It depends on all settings of all other parameters at that point in time. If you change anything else, you have to recalculate all sensitivities again. So that's also not a good property of this approach. So then you do that, and you can also go to a certain direction by taking into account the sensitivities. In fact, you can do it like this. You have the error, you calculate the sensitivities for certain parameters, and then you change the parameters in proportion to their sensitivity. So there is some learning rate here, you can say, and then you change it a little bit. So if the sensitivity is very high, then the change is bigger. And if the sensitivity is very low, the change is smaller. That's what the method does overall as an approach. I will not continue this in too much detail because we actually want to consider other methods more. By the way, if you find your, say, best setting, then it's always good, we will always ask it as well, to make a graph like this, where you put one of the states, or you do different graphs for different states, that for which you have the empirical values, and then you plot in one graph both the line for the simulated pattern and also the data. Then you can see all these deviations yourself with your own eyes, because that's very important for your own intuition to see how these actually are. And these differences here, they relate directly to that error functions, this root mean square error. So if your root mean square error is 0.1, then you can expect also variation like 0.5, 0.05 to 0.1 here. But if this root mean square is only 0.01, which is not realistic, then it would be very close, all these points here. So it's very important to always do this, because then you see really how good it is. And if you make a mistake somewhere, you see also that the mistake. So this method is relatively simple. You can have a fast convergence to some local minimum, and it's guaranteed even. But there are different disadvantages. It depends on initial point, because you are guided to certain more local minima, but maybe not to other ones that you would be guided to by other starting points. It can get stuck in a given local minima, and you need many calculations because all these things have to be recalculated all the time. So that's one method, or actually a second one after the exhaustive method. So what often happens with methods, and these are just part of machine learning, these methods. What often happens if you have the problem of getting stuck in local minima, that some random elements are added. And that's also what happens in random gradient descent. Then you also have some random changes also in the meantime that jump to other areas of your search space. So that's also something to keep in mind, that these random gradient descent or other random type of methods, they are better in finding more places where you can find this minimal, this local minima, and even find the global minimum, hopefully. So the last one that I want to discuss, that's the one that we are using. That is simulated annealing, that also makes use of a lot of randomness, and it works like this. This AP means the assignment of values to the parameters, so that's always what you have to use in these parameter tuning methods. So then you have successions of that. So this is the part that generates new values all the time for your parameters. Then there are, for each step, there are two possibilities. You calculate all the time these errors. So the first possibility is that the new error in for the new assigned values is less than the old error. That's an improvement. So you are happy when you see this. So then in that case, you always accept the new points. But there are also cases, because this has also randomness in the choices, a bit around where you are, you just choose some random way, some values. Then you can also have the situation that the error of the new assignment would be bigger than the old error. And that's by itself not good news, but on the other hand, this could also provide a good reason to jump to another place, because you never know, maybe this is not the best direction that you would go. So therefore, in this case, there are two options. There is, with some probability, you choose this still as the new point, even if it's less optimal, but just to explore new areas of your search space. And there's still also a probability to not accept it and to keep the old one. And this probability depends on certain things. That's the exponential function of minus the delta E, which is the difference in error. So if the difference in error is very big, then this will be smaller. And divided by T, and T is the temperature. Simulated annealing is based on a metaphor that comes from physics. When you decrease the temperature of some physical process, well, you know that particles are moving fast if temperature is high. They're moving slower when the temperature is more lower. And even if at the absolute 0 point of temperature, then everything would be in rest. So that also is used here. This temperature is first very high in the first phase. That means that this is a small number, so that this is close to 1, this whole thing. But during time, you let this getting lower to 0. And if this approaches 0, this becomes very high. And if you have a negative exponential function of a very high number, then it becomes 0. So later on in the process, you will have a very low probability to choose for this, say, less optimal points. But in the first phase, you use it to do exploration of more areas of your search space. That's the basic idea. Of course, you don't need to know all this formula, but this is at least to have some idea of what is in the machine, because the machines are doing all these things. So you can generate new candidate sets, and then you slightly change them. You can see this. And also, if you want to work with it, you can even read it again. So that's something that comes from some physical domain. This temperature is cooling down, and that controls the probability of going in the right direction. Uphill would be better and downhill would be worse, but that means downhill means higher error, and uphill lower error, but that's a bit, the terms are a bit contradictory here. So that's the idea, and then, well, maybe I can just show you an example of it. Let me see. So finally, then the advantages and disadvantages, and then I will show an example of it. So this can be used for models with high numbers of parameters. Groups of previous courses have done it for 50 parameters of their model, for example. But for 10 or 20 parameters, it's very easy to use it. But for 50, it's even also possible. So if the temperature decreases in the good pace, and hopefully the tool will do that, then you get also a good answer. But the disadvantage is that it's in principle slower than other methods because of all this gambling. There is a lot of gambling in it, all these dice that you're throwing or the machine is throwing that gives different directions. So there's a lot of back and forth as well. But yeah, you can have a good chance to get the global optimum. So before running it, I will show a bit how the template works. So you remember this picture that I started with some time ago. So this is what the MATLAB Optim tool dus. So you can just type in Optim tool and it should come. If it's not coming, then you have to add some tool extra to your MATLAB probably. But if you have the right version of MATLAB, it should automatically be included. And then this template is a template that I've developed, supported by some others, among which Niemand. And so this is from the MATLAB optimization toolbox, and this is the tuning template that you can download. And this is the start and stop, so you handle it through this. And this is just a kind of thing that is triggered by this one. And let me see, yeah, so what you have to do, you have to prepare that tuning template, of course, because you have to make clear what parameters you want to have tuned, and that's done in the tuning template. So specify which of these characteristics in the role matrices you want to indicate, and you specify it by putting these indicators P1, P2, and so on. I will show it in a minute. So very important, this tuning template cannot be used separately to generate simulation. You have still to do that by the older templates, not by this one. This is only to be used by the Optim tool. So let's see the role matrices. This is an example. I think it's an example of assignment. No, it's of yeah, assignment 5 or the lecture for assignment 5, chapter 4. And so these are the role matrices. So they're just one model. You see it's an adaptive model. There are also some adaptive characteristics. By the way, adaptive characteristics cannot be tuned because they are adaptive. They already have their own dynamics. So therefore they don't count. So this also, the MB matrix, you don't tune that because this has also a different function. And also these adaptive parts, they're excluded to tune them. That's clear, of course. So then any of the other numbers, you can choose it to be tuned. Any of them, or all of them even. If all of them is less than the 50 that I mentioned, so that should be even possible. And how do you do that? Just to write P1 and so on in the right places. First, you have to get rid of the values. So you leave the values out. And of course, also this adaptive thing. Then you write P1, P2, P3, and so on. Starting always with P1 and always an order like the next 2, and then 3, and then 4. And you just count further over all matrices that you want to involve. So also here, then we have 4, and then we have 5 there, and 6 there. And then these are just for the speed factors. These were the connection weights. You can also include even initial values, also possible. Then you also add them there. You can, maybe you want to check whether the Euclidean function would be a better function for this BS state than your logistic one. So then you can choose 2 of them here. And don't forget then to set in the places where you want to check it later, also the parameters here, because otherwise you don't have the parameters right. But then in this matrix also you can just number. So now I've numbered from 1 to 16. All numbers between 1 and 16 should be there. If you only want 8, then you stop after 8, of course. So you just choose what you want. So these are the tuning matrices. Just a third type of matrix that we have to use when we want to do the tuning. And if you have that, then the system knows where you want to have things tuned. So that's the information that you want to give to the system. That's actually the only thing why you do this. So then you have to copy them to MATLAB, to the MATLAB template for tuning, the tuning template. Then of course you have to leave out the P's, like we often also leave out the X's if you have adaptive model, and also put the nonce for the empty places. You already know all these things, and then paste that in between the MCW tuning matrix. So there is the tuning matrix for every role. So this is for the connection weight role. You copy it just here, and then you know already that MATLAB will accept that in the manner that you want. And then finally you have this. That's all. That's all you have to do. So these tuning matrices, you can copy them in a very similar way as you are copying also adaptation matrices, for example. So that's that's all. And yeah, this is a bit of how it works. You can see that here these P things are just taken, and then in the matrix you are just place it in the right place of the matrix. That's what, but you don't need to do this yourself, of course. What you still have to do it yourself is that you have to also specify the data to which you want to compare. So that's another part of the tuning template. For example, you have 5 time points for which you have data, and you have a selection of 3 states where for which are the data about. Then you have a 3 times 5 matrix, like this. And you paste them in this part. You paste all time points. The time points can be arbitrary. They don't need to be exactly successive. And also which states. So this is state 1, x1, and this is state x6, x12. You have data for these 3 states. And then this data are this one in that matrix. So that you have to add them too. In the assignment, you will see step by step how you can do that. So that's all. Then you can run it. And then, yeah, these are the things that are run then. This is how you can find out how it works, but I would not say that you should know that. So this is actually the formula for the root mean square that's also built in there. So I want to finish with just giving a small demonstration. So this is this thing, if you type Optim tool in the command window, this is the command window. If you type Optim tool here, then this should open, this window. Let me see, where is it? Again, this one. Here you have to place the right name of the tuning template that you use. This is how you download it. You can still use that name, but if you use
we can see the MATLAB
sorry, yeah,
program on your screen.
Yeah, I have to change the sharing. And that's always a bit pity. Let me see, probably I cannot show both even. Let me try it. Do you see only the command window now? Let me check whether the other window, you don't see the other window now, the new window. You only see the command window still. Yeah. So the
we only see a MATLAB. So I don't think, yeah, we can see the command window as well.
Yeah, but not the optimization tool that I'm moving now, You don't see that?
No, I don't see that, no.
Okay. Then I have to change.
Used to share your whole screen and not just one window.
Okay, let me see. Where is it? Stop share. Let me see.
If you just click share screen, then you can select screen 1 and then you share your whole screen.
Oh, the one that's already indicated there. Okay.
Yeah.
You see my whole screen now?
Yeah, we do.
Okay, that's good. Thanks for the tip. So in this way you learn more things. So this is the command window. So when you type Optim tool here, you should get the other window that I can show now too, this one. And I have selected this tuning template that you can download. And there is one example in it. And this example has 4 parameters that are tuned, and therefore you have to give starting points. Starting points is not so very relevant. There are a lot of jumps in the tuning process. So you can just take any like 0.5, for example, all of them. But what is important, you can indicate which interval you are expecting. So I gave the whole interval 0, 1 now. These parameters are speed vectors. So they can be found in this whole 0, 1 area. But if you think, no, I only want very low speed factors for certain things, you can make it very low. For example, this one here, I can make it 0.2. I already know that 0.3, whatever. And then I already know that this should be a low value. And that makes the search space, of course, also smaller. So if you know that, it's better to use it. So then there is only a start button, and then it should start. Let me see whether it works. Yeah, it runs, and now you can see here, you see how fast it runs. The iterations, we are already at 100, 200. And you see the root mean square error going here. If you look well, you see that we are already below the 0.1 sometimes. And it goes further and further. You can imagine that if you do this 10 minutes, you're already many thousands further. We're already at 1,000 now. So if you do it 5 minutes, you can imagine how far you already are. So you can really do it very fast. So the idea that it's a bit expensive computationally, it's not that bad. But of course, in this case, you only have 4 parameters, not too many. So if you want to see what the situation is, you can just pause it. And then you see here some numbers that have passed. We are already better than 0.064 here. So that's already good. And we are 2000, we can just resume it a bit. Let me see. No, it will not resume. But anyway, it should also be able to resume. But if you stop it, then you get the values here down of the different speed factors, different parameters. So it found that this x1 should have a high speed, and this one should lower, and this also should be lower. This is actually between below the 0.3, and this also is a bit low. That has been found. And you see that let me see, this one, the root mean square error is 0.045, which is, in my ID, a bit irrealistically low, but that's because there is only a toy example in it. For real data, you will be hard to have below the 0.1. So this is how it works. And there is also included in the zip package that is for the tuning template, there's also a second function by which you can write the data for the whole tuning process to Excel. Then you can see in more detail in what times, what iterations, which values you had. And you see also the pattern of these root mean square errors for all iterations. So you can make a graph of it. So that can also be nice to have such a graph to see how it becomes more and more optimal over time. Is this a bit clear? So you can just start to work on it in the assignment of today. By the way, tomorrow we don't have a new assignment, so you can also work on it tomorrow. So that makes that we can have a bit relaxed end of this week and the start of the final assignment after it. Tomorrow there will still be a lecture, but this lecture is not with new topics, but more with how the final assignment can be done, and also maybe a kind of overview of what type of topics you can think about for the final assignment. So that's, I think, the main thing that I want to discuss today.